Hi, everyone. A very happy Tuesday and welcome to our ARM Tech Talk series. This is the place for the latest and greatest in trends, technologies, and best practices on ARM, wherever that happens to be. It's great you can join us if it's your morning, it's your afternoon, it's your evening, if you're in the car, if you've got a coffee. Great for you that you could join us. We're really excited to have you today if you're joining us on Zoom or on YouTube. Today, we're going to have a really exciting tech talk from our AI partner, Stream Analyze, talking about streaming analytics on edge devices. I'm really excited about this one today. It's going to be a great talk. If you want to get involved with our tech talks, folks who have joined before know the drill with this. So just go through this. If you haven't joined one of these tech talks before, this is how you can get involved. You can tweet us, use the hashtag ARM Tech Talks to do so. We've done over 50 of these ARM Tech Talks over the last few years. And this is a great opportunity for you to learn the latest in trends, technologies, and best practices on ARM. So if you want to watch any of those tech talks, just head to youtube.com/ARM. And if you want to register for upcoming tech talks, head to arm.com/tech talks to do so. And here's the list. We've just announced a whole bunch of tech talks coming up right before Embedded World. So today we're going to be talking about, as I mentioned, streaming analytics to ARM-based edge devices from Stream Analyze. Next week, we've got a really exciting Matter Tech Talk talking about how you can use ARM virtual hardware together with Ubuntu and build using Python and Matter compliant smart home hub. I'm really looking forward to that one. There's a really exciting demo for that one. So make sure you register arm.com/tech talks. To put those on our tech talk. Right, let's talk about today. Today, we're going to be talking about streaming analytics on ARM-based edge devices from Stream Analyze. They're a fantastic ARM AI partner of ours, and it's great that they could join us. So before I hand over to Johan from Stream Analyze, if you want to get involved in the conversation, please use the Zoom Q&A box. That's in the little menu bar at the bottom there. If you want to ask a question to Johan at any time during the tech talk, then that's the place to do so. So I'm going to hand over to him now, and he's joining us all the way from Uppsala, Sweden, if I believe I pronounced that correctly. Johan will, of course, correct me, but it's great that he could join us. I'm really excited to hear from him today, as I hope you are too. So that's enough from me. Johan, it's over to you for today's ARM Tech Talk. Thank you so much for coming. I'm really excited.
Thank you, Tobias. I'm happy to be here as well, and you pronounce Uppsala perfectly, I think so. So my name is Johan Risch, and I'm a developer at Stream Analyze. I've been working here for, well, this will be my 8th year at Stream Analyze, and I've done everything from implementing our customer projects to working on our deep learning and inference engines and our distributed system with SA Engine. So I'm a bit of a jack of all trades of Stream Analyze. I usually call myself the janitor. Today's talk is gonna mainly be about our product, which is called SA Engine. And SA Engine is what we develop here at Stream Analyze. It's a software platform. And with it, we strive to enable edge analytics everywhere for everyone. And to do this, I first need to explain to you what is SA Engine essentially, and how does SA Engine help us do this? So SA Engine is a system with 4 built-in engines. The first engine is the main memory database, where you can query data, store weights, models, and user-defined functions using our query language called Object Stream Query Language, or OSQL. And this is a central part. This is like the cornerstone of our technology comes from the main memory database. And from that, we build up a data stream management system, which is also built in. And this is where you use the same query language, but you use it over data streams. But because, of course, if you want to really want to, get insights in real time, you need to work on data streams and not on batch data. So that's a very important part for us. And then getting a query language that works well with this. We have a computation engine, which is very different, makes a very difference from regular data stream management systems and main memory data.
Johan, I'm struggling to hear you at my end.
Yeah, am I back now?
You are back. You are back.
Yeah. Okay.
Technical gremlins.
Yeah, exactly. I lost the screen here for a while.
No worries. We can still see your screen. We can still hear you.
Okay, good. So the computation engine allows you to use the same query language to do quite advanced query or computations, anything from Fourier transform to image analysis to regular mathematical statistics. And finally, we also have an inference engine, which allows you as an engine to run deep learning inference with essentially any deep learning model or on any available runtime that is on the device. So we're essentially hooked into like the runtimes available on the device there. So SE Engine comes in many different footprints, well, many different, but the smallest one is 20 kilobytes, and the biggest, the full system, is 6 megabytes of RAM. And of course, when we're talking about the really resource-constrained edge devices, we're talking about our smallest footprint, which is, the SE Nano Core, as I call it, which is 20 kilobytes. It can run bare metal with a real-time operating system or any regular operating system as well, of course. So, and all it needs is a C99 compiler for the target platform to be able to run there. So that's a bit about what SE Engine is, but let's just go through some capabilities as well. And I usually call this the wills and won'ts of SE Engine. So SE Engine will allow you to query data streams in real time using on any connected device, and I will show you this today as well. And it will also run completely autonomous when needed, which means that if your use case demands it, you can run completely without connection and run it completely autonomous or offline, dug down into the earth if you want to. It will use the built-in main memory database to update models and queries without changing your firmware on your device, which is an important part, which how we can actually enable such a much higher efficiency for our customers. We'll get back to that later as well. And it will allow you to use the best and most advanced query language there is for streaming data and running advanced analytical and machine learning and deep learning models. And this is also one of the big focuses of my talk today, is that we also just-in-time compile your queries into machine code to run on the edge devices, making sure that we cram every extra bit of performance we can from our edge devices that are so constrained in today's world. And as I said before, it will use any available inference runtime to run deep learning models. We have a built-in one called sa.nn, but we can use TF-Lite or OpenVINO or any other one available on the target hardware if need be. And now, kind of important part, what SE Engine, oh yeah, of course, it will also change the way you look at and approach edge analytics. I hope that I will show that for you today. What SE Engine will not, which I usually find is more important to get out there, so we don't get miscompared or compared with the wrong type of things here. So we will never create a highly optimized and quantized neural network using SE Engine. That's not what we do. We don't update the device firmware using FODA, and we don't only do neural network inference. These like key points of what we don't want to do, and we probably never will do. So one thing SEN Stream Analyze has done a long time, actually ever since I started in 2015, we've been running on ARM devices. And I mean, in my opinion, ARM is like the only viable architecture for implementing edge analytics at scale, because they excel at everything from the embedded edges. I mean, even the smallest ARM M4, M0s, M3s, to their supercomputers, Ampere Ultras, which we've just started using as well. So they're really good in like the full span of an architecture here. And the first project we did with the Stream Analyze and with ARM, with an ARM device, was an industrial Android device connected to a wheel loader's CAN bus back in 2015. And since then, we run project where you run on Cortex M4s connected to the data bus of smart tool batteries. We run on chainsaws. We run as a co-processor to telematic compute units inside industrial vehicles, and of course, we actually run on the actual telematic compute unit on the industrial vehicles as well. And that is actually the most common platform for us still. So we're still mostly working with projects in the Cortex A7 family, and that is because, well, that is what the heavy-duty automotive industry is.
You're not back yet. Sorry, Johan.
Oh, sorry,
you can see your screen. There you go.
Yeah,
You're
there
back
we
again.
go. Okay, yeah. Where were I? I was at the Cortex 7 family on telematic compute units, mainly used by heavy duty automotive, which is where we have most of our customers at the moment. So that's why we're there. We also have 2 Ampere Ultra 80 cores here in Stockholm, which we run our scale-out tests on, which we run, simulating 25,000 edges, simultaneously doing analytics and combining data from them and doing really quite advanced kind of distributional queries daily to test our scaling out possibilities. I mean, as this slide shows, ARM is the obvious choice for us because they're like I mean, mainly they always there, and it's a very, very convenient hardware platform to do also our compiler on, which I've heard from, not from me personally, but from our compiler guy at Stream Analyze, that it's a very nice assembly to use. So that's good as well. So ARM helps us with like getting the analytics everywhere. And so what we want to do with SA Engine, of course, getting SA Engine everywhere, but also by doing that, also getting it to everyone. And that is like really one of the things that I have close to my heart with Stream Analyze, that we try to lower the bar for entry to Net Edge analytics, which, let's face it, is quite a hard problem. Actually, it's a hard space to be good at. And I will address 3 key points that keeps the bar high when entering the field of edge analytics. And the first one is it is complex to implement analytical models. You need programming, and analysts are seldom programmers. We've seen this time and time again, and programmers are seldom analysts. And this is a gap that we try to fill with SA Engine. I know, to make it all worse, at the edge, almost always resource constrained. So this usually means that you need to resort to kind of lower level programming languages, C, C++, Rust, whatever you like there. And this makes it even harder for like a analyst to do it, because they're not programmers. They're mathematicians rather. And then finally, it is time consuming or even risky to update edge devices. Will this firmware update be the last write cycle for your flash? Well, deploy and find out. So with SA Engine, we actually try to solve these 3 obstacles with the kind of the same approach, actually. And the first thing we do is that we use a very high level query language, which is declarative. And this allows for a much larger user base than regular programmers and regular programming languages. It is not uncommon in our projects that we see our project manager actually start doing queries on the edge devices, because it is so accessible for them that they can actually do this and actually start using our system on real live devices. But then the problem comes: how do you run a query language on a resource constrained device? Well, first of all, we do have a very smart query optimizer, which actually takes the query and makes a optimal execution plan, of course. And then we take a just-in-time compiler and generate essentially a combination of interpreted commands and assembly code, which can then run on the target hardware. And I will show you today that we can actually, in certain problems, we actually get better performance than what a C programmer would get trying to solve the same problem, which I think is kind of cool. This is kind of where we want to have at least be close to like optimal performance and still give our users this kind of flexibility of interactive development and model deployment that we actually supply to our customers. And then finally, I mentioned here, by deploying models to the main memory database of SA Engine, we never update the device firmware during the analytical process. This allows the user to get close to instant feedbacks on deployment and model execution during this analytical cycle. And all of these points here kind of goes into my next slide, which is the software cycle versus the analytical life cycle. And this is like one of the key problems that we solve with SA Engine. I've seen this many times. I've seen this in all my years working here at Stream Analyze. I've seen it time and time again, that the analytical life cycle is always at some level dependent on the software life cycle. So essentially, you always have a you have your modeling, the evaluation, refine, and then once you're ready to deploy, you need to wait for a software cycle to do deployment, which has its own cycle of deployment, testing, refining, and then deploying again. And especially in the automotive industry, you have problems where the deployment might take time because you need to certify your software. You have a code freeze. You might actually have a code freeze a year in advance before the deployment happens. There's a lot of problems here to which is really hard for data science teams to get their models out on edge devices like this. What we do with SA Engine is that we put SA Engine in on the hardware with one regular deployment. After that, you update during the process. You update SA Engine using the main memory database, which means you can deploy models at any time you want. I kind of compare this at doing this old way with having a firmware update to get a new model. That is kind of like keeping the stock and price information of your web shop in the Java code for the web server of the web shop, while we put when it should be in a database. We kind of do the same thing with SA Engine. We put the analytical models and the algorithms you run in there in the database rather than in the firmware. Okay.
You are back now.
Yeah.
There we go.
I'm terribly sorry for this. Let's see here. It's the mouse as well. There we go. That is okay. So I need to use my trackpad and stuff. Yeah. So that's kind of what we do. We put it in the database instead. And we've actually seen with many of our customers, they come and say that what took them 1 year to do before get deployed on a hardware, on an actual machine or a truck or a reloader running in a factory or in production, took them 1 year before, can now take them 2 weeks. We're getting like a more than 20 times speed up in the analytical workflow process for these kind of engineers in the back office of our customers. And that is like really the core for me as a developer, what I really like to supply for our customers, that we help them get their things out much faster in a much easier way as well. And that's kind of me motivating what SE Engine is and why we do it. So let me show you, let me get my hands dirty a bit here and show you what I mean with the performance of SE Engine. So for this, I'm going to use a classical problem called send more money, which is a verbal arithmetic, which means that each letter is a digit and no two letters can be the same digit, and the leading digit of a multi-digit number must not be 0. And this is, maybe not a typical problem that we use in our edge devices. We usually work on streams, but it's a quite compute intense problem, and it's actually a search problem if you think about it. It's trying to find the solution to this equation. It's kind of like a search problem. So we've compared 5 systems. We will, of course, compare the SE Engine. The gist here is it will be updated later this evening with an updated version, because I actually did a change this today and updated it. But you will be able to look at the source code of my tests here as well afterwards. And then, of course, I compared it with C, because C is usually like the alternative. When we go to customers, they have embedded teams who want to do the modelings, and that is how they. Then C is also one of the kind of competitors for us. Also compared to Python, because that's the other side. If you talk with analysts or engineers or data scientists, they use Python. So when I compare to Python as well, to see the difference there. And as I said, it is a constrained programming problem. So it wouldn't be fair if I didn't compare it to like a constraint solver. So I used G code, which I've heard is one of the better ones out there for solving constraint problems. It's a C++ library or a C++ system where you generate programs to solve these kind of problems. And I also compared it to PostgreSQL, which is kind of funny if you think about like resource constrained edge devices. But from our perspective, where we come from a database background, it is quite interesting to compare us to these kind of databases as well, to see what differs our optimization technologies from theirs. And that's the same for G code, because SE Engine is essentially like a combination. We do have a bit of constraint solving, and we are a database, but made for data streams. So we do have like a bit of these technologies of all of these kind of platforms in our technology. So from our point of view, it's quite an interesting comparison, actually. So let me show you then, start showing you this demo I'm going to show where I show you how I got the benchmark numbers, essentially. So first of all, I'm just going to look a bit at the problem here. So the problem is that you have 9 digits, send more, the letters, and you have send plus more should equals money. The solution is what you see here, and this is just a control. You can see that this actually adds up to this. That is what we aim to solve with our problems here. And just to start, we can start with a very, very basic solution, which is an A1 in Python, where you essentially do for each number in range from their 1 to 10 or 0 to 10, check if they add up to the right values here. Of course, this one is super slow and it's not very efficient, because it's run only in Python iterations. So of course it's slow, but it's just to show you one algorithm for solving the problem. We just do a brute force search. In SE Engine, you can see this as said on the gist slide, but essentially we have a couple of helper functions, and then we have the actual send more money here. So you're going to get a glimpse of how OSCAL works here, but essentially, we select the send more, which are all integers. We say that this equation here should hold, that the send plus more plus money times the 10 potents of each digit. All of the digits should be different, and all of them should be digits. And all digits essentially says that every number is from range 0 to 9, inclusive. We add the two last constraints that M and S are at the start of two multi-digit numbers, so they need to be larger than 0 then. And that's how we define the solution to this problem. There was actually two other solutions I found in the wild. One common in Python was that they actually had that that MX1, because I can never have a carry larger than 1, so we could add 1 here as a make it easier to solve, because you're actually reducing your problem space by one of these outer loops. And the last one actually got from G code, where they had a carry linear algebra over the carry bit rather than doing the actual equation of send more money. And I just copied the same solution they had there, which essentially is like a bunch of digits here. These C's are digits, the carry digits, which are then carried over, and we do the same kind of rules there. I just took that from the G code example. And finally, you'll see that I just time this function. So I run the send more money 100 times, and 100 times, and the linear algebra 1,000 times. And 0 to 0, 1 is the base time, and that is the time that it took for C to run it. I will show you that as well in a second. So going here, I'm on my Windows substitute for Linux here. I'm just going to show that we have the same file here that I showed you before, but in Linux. I'll do se.engine. I will load this smm.osql, and you will see that we have a 0.007 seconds for the basic one, 0.099 so you need to divide by 100 here. So you have a 0.0009 for the M1, and the linear algebra one had 1,000 times on the 1.66 seconds. So that is 0.0000016. That's for SE Engine, how we did it with our system. Next up, I'm going to show you the C solution. I'm not going to go through this solution in detail. It's also available in the slides, so you can look at it yourself. But needless to say, it is more complex. I actually did not bother to do the linear algebra or the M=1 solution for C, because we're kind of proving a point that we don't want to. We want to have it easy to do this. We're trying to lift the bar. It should not be hard to change these rules. If you're adding like a small set of change for the rule for your problem, it should be fast and easy to do. So in C, we only did the solution we found in the wild. And he tries to be quite smart with like swapping digits and doing it in an efficient way. The original solution did a return actually and ended as soon as he found the solution. Actually, you need to do the benchmark correctly. You need to search the whole problem space to find, because you don't know how many solutions there are. And I actually just modified the C file in this benchmark to just not return when you find a proposal, and always going to go through all of the possibilities. And of course, we GCC this file, which is GCC 03, and we'll do smm.c. And as you see, of course, right now I'm running on my laptop, which is an x86 processor. But at the end here, I will show you how we'll do the same problem with the engine on an ARM Cortex M4.
Apologies, folks. We're just having some technical difficulties at Johan's end. Hopefully he'll rejoin in a second. Yes, just apologies about that. Johan's just had an internet connectivity issue. He'll be rejoining shortly, where he'll walk us a bit through the Stream Analytics platform. In terms of, as we're just going through this, if you've got any questions for Johan, please don't forget to put them in the chat, in the Q&A box rather than the chat. That'd be amazing. And then we can get to those at the end. Johan's then going to show us the Stream Analyze platform and how it integrates with ARM. So do make sure you stay tuned for that. It's going to be a really good demo shortly on this. So he's just going to restart his laptop. He'll be joining in 1 minute. So please do bear with us. Appreciate that sometimes we do have some technical difficulties, and we're just encountering these at the moment with Johan and his system. So please do bear with us. We'll be back online shortly. If you have got any questions, please do put them in the Q&A box, as I said. As I say, appreciate you just bearing with us just while he rejoins. It shouldn't be more than a minute or so. I've just heard he's had the dreaded blue screen of death. That's always the way. So we sometimes have these in Tech Talk. So it's just the way it goes. You know it's live, right? You know it's live when you have sometimes these issues. So please do get through. So. And just, I actually did forget to say to folks at the beginning of the call, if you do miss any part of this Tech Talk, then the recording and slides will be available immediately after this session. So if you do miss any of it. So Johan, blue screen of death.
Let's see.
The demo gods were shining up until that point, relatively so.
Yeah, exactly. Blue screen of death here. So yeah.
No worries. Do you want to re-catch up where you were on the...
I think so, yeah. Where did you lose me?
We just lost you as you were going through the bit of the seed demo just at the end there. So.
Yeah, okay. So let's see here. I just removed all of my peripherals now, so I'm using my laptop, webcam, and everything to reduce the risk.
That's fine. It still looks and sounds great. So I'll go on mute and back over to you, Johan.
Yeah, thank you. Okay, so so this was a C solution. They tried to be smart, and I was just about to actually compile it on my VSL2 here. So let me just go to VSL here and do development, CD demo, CD ARM. Okay, then, so let's see, let's zoom in this a bit so you can see what I'm doing. Look at this maybe. Okay, I was actually afraid I would talk too fast and to be too fast in this talk now. Now I actually gained 4 minutes, so that's good. Anyway, let's see here. We look at the file here. So what I changed in the C file for the test is that I made it run through all of the solutions, and I removed the print until the end. Well, no prints, so we don't lose performance to the stand out there. And then we'll compile this with GCC. Oh, let's see here. I need to have American. There we go. There, GCC-03 smm.c. And I will time this a.out. And the astute of you would think that, well, now I'm actually starting a program and timing the starting and termination of a program. When I recorded my numbers, I took this execution time, which was actually, let's see, 1.1, 1.2. And I removed it with the time of just starting the program, where I just removed and just started the a.out and exited straight away. So I removed the startup time that way, which, by the way, was about 1 millisecond in time. So that was this for that problem. And now we actually need to bring up the. I actually forgot to bring up the presentation here. I'm gonna go like this, and we'll just do like this. I'll have to do without my notes. So we're here. Let's go like this, and now we go back to the next problem, which then is the Python solution. In Python, we do it like we use iter tools and do permutations. We take our digits and our characters and permute them in all possible ways, and then we try to find a solution where they work, essentially. And this was actually the fastest Python solution I found there out in the wild. Then I also managed to do it with m=1. And that is what I'll run here. So I'll just do Python 3 smm.py. And you see what we get there is 2 seconds, 2.7 seconds, 2.4 seconds. I actually got 2 and 0.2 on when doing this without sharing my screen and everything. So we might get a bit worse performance when doing this, of course. Yeah, and then finally, the one that beats us is of course the constraint solver. But as I said, it would not be fair to compare this problem without having a constraint solver. So this is the G-code example. They're built an example for Send More Money. A big difference though is that I actually added this one. I added the M1 model myself then, where because of course being a constraint solver, even though it's C++, it's quite easy to just add a rule here, which just shows that even though you have a low-level language, having a high-level abstraction actually helps you to solve a lot of these problems of making them easier to solve for a non-expert. Because I only spent like 5 minutes inside G-code and managed to actually add this rule anyway, which I think is also a good point of having a high-level abstraction. Anyway, what I do is I will run the G-code the different models, and I will just grab the runtime, and we'll see it like this. And we'll see that we have, okay, so this is actually lots slower this time than we had on the benchmarks. The runtime usually was on 0.4 or something milliseconds. But that's the time we're getting in we're running here. So of course it varies a bit. So that was it for G-code, and now I've shown you all of my runtimes. So I think we're back to here. I will not show you Postgres because I've actually uninstalled Postgres on my VSL2, so I could not do the benchmark again here, sadly. But it was much slower anyway, it doesn't really matter. It wasn't really on par with what we're measuring anyway. So anyway, this is the results. See if I can actually move. Can I actually hide my camera here? It's kind of annoying. There we go. The results we got there for SE Engine, we had like for SE Engine. Wait, let's see. For SE Engine, we had the regular solution was 0.05 seconds. M1 was then 5 to the power of minus 10, and the linear algebra was 8 to the power of minus 5. 10 times 10 to the power of minus 5. C got it to 0.01 in the runtime when we had the O3 argument added there and reduced and removed the starting time of 1 millisecond to the program. Python at 2 and 0.2 for the M1 and regular, and G code was consistently better at 2 times 10 to the power of minus 5. But that is also to be expected because they are a C++ based system that is made for solving these kind of constraints. So they, of course, I mean that is kind of expected. But as you can see, we can actually get at the comparable performance or at better than C on these kind of problems, which I think is kind of cool without having to deal with any of the low-level details of writing the C code. And that's what I'm going to now, because I'm going to show you how we can go from one of these high-level queries and run them on an ARM Cortex M4. And what I will be using here is this ARM Cortex M4 board from STMicroelectronics. And first, I'm just going to show you the logic and how it works. So first, we take a query. So we're going to take a query where we select the signus of each integer from 1 to 10. And we're going to put this through our query optimizer. And inside the query optimizer, we do a bunch of things. We do rewrites, we do logical rewrites, and we substitute different parts of queries to kind of reduce computation. We do quite a lot of things here, which are quite cool things happening actually. And one of the things we do nowadays as well is that we make sure that we group our different program or different instruction parts into groups so that we can compile them as one big blob of assembly if it's possible. But anyway, output comes from this is a so-called streaming logic program, a slog program, which essentially is a typed, kind of like a typed object log with our own touch on it. So where you can actually say an instruction for our slog runtime to run this. And this is actually executable now, but it would be fully interpreted and not very fast compared to what we're going to do with it. Yeah, so that's the slog execution plan. We will then take the slog execution plan and pass that through our query compiler. That is a JIT compiler, which will actually translate this into a so-called slog plus slap execution plan. Now that is a streaming logic assembly program, which essentially means that we have the slog up here, and then we just call some binary, some machine code in the middle of there. So what happens with send more money is essentially that we essentially just get one of these call slap, and all of this here is just assembly code after that running there. And then, of course, if we running this on, we support most ARM devices. If you run like an ARM v6, I don't think we have assembly for it. But then we have a generic assembly which we run in an abstract machine, which essentially makes we still get quite a good performance compared to like doing like regular interpretation of slog, but it's not as fast as machine code. And finally, we just take this slog and slap execution plan, put it through the slog runtime, and out comes the results, like magic. So that is how we go from a query to the results of a query in a very high level way. And in details for running this on this board here, I'm going to show you, we actually do it like this. So we have an SE Studio somewhere, can be on a company PC server or in our SE Studio environment up in the cloud. And we have a relay process, an SE engine running somewhere close to the chip where we have an RS-232 cable connected to it. And this is where we run the query optimization and the query compilation. So this is where we generate, based on a text input from the studio here, we generate a slog and slap execution plan, which is pushed down to the slog runtime running on the SAME 54 in this case, which is a microchip device, which we've done together with them in a partnership for like analyzing motor control. The slog runtime runs its stuff and it does the models based on the local database and the sensors and what's happening, and results will be pushed up to the relay process, which will then push up further up to the user where they entered the query. Of course, this is the interactive way. I told you can also run them completely autonomous or offline, and this is how that would look. So essentially, you will take your slog and slap plan and put it in ROM, essentially a C string. And it will essentially do like SA evaluate on the pre-compiled query string with a callback function, which is a C function where you just get all the callbacks when data is produced from the model. And then of course it's up to you what you do with these kind of models. You can do whatever you like. So before I show you this in action, I'm just going to talk a bit about the footprint and what we say when we say 20 kilobytes of RAM in footprint. So like to the left, you have general footprint of SA nanocore, which is kind of like ranges, and to the right we have the minimal memory to boot SA nanocore. So to boot as a nanocore, we first need 204 kilobytes of text and data, and we have part of our system image, which usually resides in RAM on our larger devices, we now put statically on the flash. So that's 67 kilobytes of image. Then we need roughly 5 kilobytes of image for the dynamic part of the image in the RAM, and we need 5 kilobytes of static memory. And I think like the minimum stack you need to boot is like 9 kilobytes of stack, and that's why we say 20 kilobytes is the minimum, because with 1 kilobyte more of C stack, you can start running some models as well. So that's like that's where we get the footprint from. Anyway, now it's time for the second demo of the evening, and now I'm going to show you how we can do this, run this queries against my my Nucleo board here. And I think I have to start everything again, but luckily I actually have a helper script which essentially connects here. So I start an SEngine relay process, which actually has now connected as a micro edge to my Nucleo board here. And I'm going to open a notebook here. I'm going to run this using my let's see here. I'm going to reopen it with our notebook or our VS Code plugin here, so we can run this as a notebook. So for instance here, the first thing I'm going to do is just send a query to the peer micro edge. I'm going to send the query 1 + 1. What will actually happen here, you see that first we sync up to try to get in sync with the edge device, and you'll see here actually a trace of the serial line on the device here. So you see me posting down a code block here essentially, which is the code being run on the edge device, and back we get a 2 here. This is the example I showed you there. We have the select, the x of sinus from integers 1 to 10. We can run this, and back we'll get a line like this. We can also, of course, change this to 100 if you want to, no problem. Run this again, and we'll get a larger curve and more data coming up there. And then, of course, we have the send more money on the Cortex M4 here. So just running this program here, we'll get the see the code. You can see that quite a large code there, and we got the result here: 9567108 and 2 in 1.9 seconds. I think it's usually like 0. Yeah. There's a bit of a overhead, of course, of running the query of the series. As you can see, that we usually have like a delay here of 0.3 seconds at least. So have to reduce that to get the execution time on the edge device. And of course, we can run like the linear algebra version as well, which is faster, and we'll run that in 2.4 seconds this time. So yeah, 0.5 there. So that's how you can run this like in a notebook-like fashion. I'm running this directly on this edge device here, like on the ARM Cortex M4. And one important thing to note there, and like in this case, we're using a serial protocol, RS-232, but it can just as well be any type of bidirectional communication, be it cellular, Wi-Fi, Bluetooth, anything. Just some way for us to put these kind of bytes down to the device. We can do this in a more distributed fashion as well. So that was it for the demo, and like this is just like my final slide. We're going to talk a bit about what's next for SEngine. So one thing we're continuously working on compiling more and more slog to slap. The latest thing we did was that we can almost define full convolution over images in OSCAL and fully compiled. And while the compiled code is not as efficient as cache line optimized C code yet, we're in decent performance, like 4 times slower than C, and you can do full image filtering and blurring and these kind of convolution operations on images in the query language, fully in the query language, which I think is kind of cool. We are going to optimize SA nanocore for flash size. As of yet, we've only optimized it for size in RAM and nothing in flash, so we still have a lot to do there. We are going to add more off-the-shelf hardware platforms for users to test on. So, we have a goal of having 10 more platforms, MCU platforms to run on in the coming 2 years. One thing I'm working on is actually improving the UX of the setup for this. Now you saw me, I had just a script to set up my relay process, but I want to put this like in a website with using a SEngine running in WebAssembly to kind of like connect to Serial port and get it really running straight from our web UI. And one thing that's what we're going to do is like generate a utility program to generate these kind of CAN-C programs. You kind of get like a skeleton program from a skull model that you can run on your target hardware. So thank you for bearing with me through these kind of buggy Windows experiences and some demos. I hope you enjoyed it.
Thank you, Johan. Look, it happens, right? This is it. Show, as I was saying to the audience just before we joined, this shows it's live, right? These things happen when it's live. There's no pre-recording we can and another take we can do and another cut we can do. This is live. It happens, right?
Exactly.
It happens. So the demos work really well, and it's been a great talk. So thank you, audience, for sticking with it and bearing through those technical difficulties. We got there, right? We got there. So now it's time for Q&A. My favorite part of the talk, arguably, because you guys get to ask your questions. So please use the Zoom Q&A box to do so. As usual, I've got a couple. But before I do, I understand you recently got a really exciting news about a grant that you've secured. Do you want to tell us a bit about that? Some really exciting news for the company.
Yeah, so we got accepted into the EIC Accelerator program for, I think it's Horizon 2025 it's called. So we got quite a big grant there from the EU for continuing working on SA engine and making it run on smaller devices more efficiently. So it's going to be 2 years of fun, and actually that's where we get the 10 more hardware devices from. That is part of the project there, to port to 10 hardware to 10 MCU platforms. And we've already looked at them, and most of them are ARM-based devices as well. So that's good.
Exactly. That's great news for you guys. It's great for us, to see you deploying further on ARM-based devices. It's just awesome, and even more constrained devices, right? Mm-hmm. I mean, in terms of more constrained devices, do you plan to support a Cortex M0 based device?
Yeah, so actually, I think we actually support it still now as well, but it will run the generic assembler, not the compiled. We don't generate the assembly version of M0s, but we do run it. The thing is though that of course they don't have enough views, so you will need to run all your models in integers, which you can do. So this is something we will support more openly soon, but we have run on it and it works, but it's some kinks it works out still. So
sure, absolutely. And how could the audience actually get involved and try this out on their own? Have you got anything you can tell them about that?
Yeah, so if you go to studio.streamanalyze.com, which is our studio webpage, you can actually just register for free, and we'll boot up an SC Studio instance for you in the cloud, and we'll be able to test this on any of your larger base devices like ARM Cortex A7. For the Cortex M series devices, we're still doing that with partners and customers only, but get in touch with me or our COO Daniel Spar, and we'll set you up if you're interested in testing it out. So yeah.
Amazing. Thank you, Johan. And feel free, by the way, I think we can stop sharing your screen if you want to. No. And hopefully, I don't think that was the problem anyway with the demo. So, but no, exactly. That's cool. We could just talk about that. And actually, while you're doing that, if you wouldn't mind, someone's asked, Pietro, and apologies for mispronouncing your name, Pietro, has asked if you could give us on chat the GitHub address from StreamAnalyze.
Yeah, we don't have we don't have much on GitHub public yet, but I think we have like the MQTT broker publicly, but I'll give it to you here. So it's we'll hear in a few seconds.
Thank you. And yeah, do please get your questions in. If you've got any other questions.
Type answer. There we go. I'll type the answer to you, Pietro. There we go.
Fantastic. Thank you. And there you go, audience. You should also be able to see that on the Q&A box under answered. So we're getting a thumbs up. So it's all working good, which is great. So we've talked about how you can use StreamAnalyze in your workflow. What about multiple models? Could you discuss about how multiple models could coexist in these edge devices?
Mm-hmm. Yeah, that's a very good question, and it is. I mean, we're running on the ARM Cortex A7 family devices, of course. Then we'll run them in pthreads because we run on Linux. If you're running like an real-time operating system, like an RTOS, like FreeRTOS, we will run them in their tasks there. But we haven't. So what we're looking to now is also running them simultaneously on even small, bare metal devices. And before, 1 year ago, our footprint was so big that it wasn't really possible to run more than one model anyway on these small devices. But now we're getting to the size where we actually can run several models even on quite small devices. And we do this actually now by doing like a kind of like a hack, or we do like stack unwinding. So we jump down the stack and we start SE engine there, and then we do a long jump back up to continue the main processor. And that way we can run one SE engine query and a separate system at the same time. That's how we do with Microchip, where they have a motor control and we run a SE engine at the same time. So we go back and yield to them at regular intervals. This can of course be extended so that we can use so we can have several tasks there, like splitting the stack in several sizes and running them and jumping between them. So we can run not parallel, but at least simultaneously. And then of course on the ARM-based devices, you can also utilize that to have both a main stack pointer and a program stack pointer. So you can actually, just allocate a heap area for the SE engine stack and just put the program stack pointer there in an interrupt routine, and then you would actually get preemptive scheduling of these tasks as well. So we've done some experimentation and know that it works, but it's like, I think we're not really there in releasing it yet, but we know that it works at least. So it's gonna be coming soon.
Amazing. Thank you. No, that's great. That's great. And, do get in touch if anyone's interested. Please get in touch with Johan as well. They're part of our ARM AI partner program. So it's great to have you guys talking today to our audience. So, and thank you again. Last chance, audience, just to get your questions in for Johan. And also just a reminder that next week we've got a really exciting tech talk talking about all things Matter with a demo featuring a smart home hub using Ubuntu and Python. So do check that out. And make sure you register for that as well. You should be directed to arm.com/tech-talks to register for those, and all the other talks should be live either right now or straight after this. And indeed, the slides from today in recording will be live within the next 24 hours. Certainly, the recording should be live immediately on YouTube. So if you've missed anything and you yourself encounter technical difficulties, then you can of course just watch it back and tune into the bits for you and talk to Johan and the Stream Analyze folks. So I think we're at time. This is at time now. So Johan, really appreciate you guys preparing this presentation. Great content today, and not just one but two demos. I always love more than one demo. That's always great to hear. And we got through a really great presentation today, and I hope audience you've learned a lot. Johan, is there anything you'd like to add before we close today?
No, lovely being here. Thank you for having us, or having me at least. Yeah.
No, great to have you. Thank you ever so much, and hope you've learned a lot, audience. And great. Thank you so much for your questions. We look forward to seeing you next week at the same time, 4 p.m. GMT, 8 a.m. Pacific time, for another of our ARM Tech Talks. See you then.